On the campus of Stanford University, the world's largest linear electron accelerator is taking shape. Essentially an electron microscope 2 miles long, it will permit man's most refined exploration of the atomic nucleus.
My name is Theanne Schiros, and my science is chemical physics. Physics is a discipline which seeks understanding of the laws that govern nature and discoveries of those laws. Chemical physics is a study of chemical reactions from the point of view of physics. We're studying how you can make hydrogen as an energy carrier by using sunlight to split water into hydrogen and oxygen. Using the synchrotron light, we can zoom into that interface to really study the fundamental things about that reaction. Synchrotron is actually a particle accelerator. It's a circular particle accelerator. You can think of it like a car screeching really fast, screeching around a track. It will give off kind of a cone of sound. And in the same way, a charged particle, when it accelerates, gives off a cone of light. And right here we have the storage ring. It's a circular building encased in cement to make sure the radiation doesn't leak, where electrons are kicked out by an electron gun and then accelerated to close to the speed of light to provide electrons for the ring. The electrons get into the synchrotron ring by traveling down this pipe into the larger synchrotron ring, which is very similar to that one except much larger. It's 80 meters in diameter, and it actually extends all the way around the facility. Off this ring are pipes called beamlines, and these beamlines deliver the synchrotron radiation to the scientists where they can direct it and hit their sample with it. I'm using the synchrotron to probe interaction at interfaces, and the interface that I'm really interested in is between a solar cell and water while sun is shining on it. We could power the planet with hydrogen, which when it combusted, you would get water. So you basically would use solar energy. You would power the planet with sunlight and water. You would generate hydrogen from water using sunlight. The holy grail of chemistry, powering the planet with sunlight and water, living truly within the regenerative capacity of the Earth. In order to look at the solar water splitting reaction, we actually have a glass cell where we immerse a solar cell in it and connect it to 2 other electrodes and shine a light on it. And the light actually excites the electrons where they pass through the solar cell into the water and split it into hydrogen and oxygen. And you see the hydrogen bubbling at the semiconductor, and you see the oxygen bubbling at the platinum, which is the counter electrode. So it's a 2-step reaction. And then we study the changes in that sample compared to the sample that hasn't produced any hydrogen. We can actually kind of take snapshots of the reaction. So we might do it for 8 hours, we might do it for 20 hours, and we always compare to a reference sample. And in that way, we kind of get the pieces of the puzzle. We see how the atoms at the surface have changed, how the surface has changed. And all of this we can see with our synchrotron light. The synchrotron radiation that's delivered, it's white light, it's all the colors. So this gigantic monster is our monochromator. It's an energy selector. It lets us choose the energy, which is the same as the color or wavelength that we want to hit our sample with to study a particular thing. Everything has a characteristic energy in nature. So by this way, if we want to study the binding energy of an electron to a nitrogen atom, we just tune our monochromator to that energy, and then we can probe that very thing. We travel along the beamline, we see it's covered in aluminum foil. And this is kind of maybe a curiosity. There's all this high-tech equipment, yet it's covered in aluminum foil. And that's because these beamlines require vacuum. And in order to maintain that vacuum, we need to bake the system, just as you would bake anything. Wrap it in heat tape, heat it up. The molecules that are stuck on the surface get kicked off the surface by the heat, and then they get pumped out with all the vacuum pumps that you kind of can hear whirling around. And at the very end of this beamline is our end station where we actually look at our water splitting samples. We mount, actually, samples that look like this on a sample holder. So we'll look at a number of different samples before and after corrosion. And then this is actually a manipulator rod, which allows us to transfer our sample into this part of the chamber. And this is the prep chamber, where we can do also additional sample preparation. We can dose gases that we have here. We have oxygen, hydrogen, number of gases. So we actually can dose gases and do reactions on the surfaces. Right here, we have a detector that actually catches the photons. On the other side, we have a detector that catches the electrons. So these are a little bit like the eyes, the ears, and the nose. These detectors are the senses that let us understand what's going on in our sample. What we get out of that is actually a bunch of wiggles. And we actually really need to kind of deconvolute those wiggles into what they mean, what's changing. These wiggles on my screen right now are actually the information our detectors give us. The thinner line is actually after 8 hours of hydrogen production. This kind of spectra can tell us that after hydrogen production, what does the nitrogen do? Well, it looks like the nitrogen stops being bound to gallium and starts being bound to surface atoms, including oxygen and other things that are in the water that we do the reaction with. And so each experiment we do, we get a new wiggle, we get a new clue. And then we have to step away from it, spend some time, at the computer analyzing and trying to understand what's going on. And then we say, I think, in this reaction, the nitrogen in the material rushes to the surface and protects it. It looks like after a while, we have more nitrogen at the surface than in the bulk, for instance. Well, maybe, but there's so many things going on in nature that maybe it's something else. So we do then the next experiment where we actually specifically probe the nitrogen. And we get some information and some wiggles about the nitrogen, and then we sit back. And so, little by little, each experiment gives us a piece of the puzzle, and eventually, kind of the story evolves. I was working in an art gallery. I'd studied liberal arts as an undergraduate, and I just felt like there were so many things that one could help with. And I started thinking about renewable energy and how we use energy and what we're doing to the planet. And the more I learned about solar energy, the more I realized we really need a better understanding of the technology to make it a reality. I mean, every hour, enough sun hits the planet to power the whole Earth for an entire year. It's our job to kind of capture it and convert it and use it. So I really wanted to study solar energy. And as I kind of started thinking about solar cells, I realized you need a PhD in physics to do that. I think sometimes it's really unfortunate kids get this idea that they can't do something, or if they're not really good at math, that they're not going to be a good physicist. Of course, it's important to take your science classes. I think equally as important is to stay open-minded about the different things you could do with those classes. Some of the best physicists I know are not particularly talented at math, but they have some determination or some insight or some different level of intuition which makes them really unique and good at what they do. You're getting a little bit of truth. That's the excitement for science for me. The truth can get very blurred in modern times, but when you see something happening, it's the most fundamental level of how we interact with our planet, and it's kind of the luxury of getting to spend my days studying that is what I find really, really exciting.